morning 8 to almost. Okay. Okay, so let us start. So this is where we ended last time, right? The left hand side here was the correlation of the voltages recorded by two antenna pairs or one antenna pair. So that can be all the antenna pairs possible in an interferometer. Like for example, GMRT has 30 antennas, so we'll get 435 such pairs. So that is what is this at a given time, and then the location of the antennas or XA and XP, and the frequency or the angular frequency is omega. Right? Now this is related to in the right hand, the entire right hand side. What is coming from this sky is what is not level, which is this I as a function of Ni. which is something which is the property of the sky, right? But then what I measure, not only that, it has all these other terms. Let's go through them one by one. So we have this time dependent gains. So remember that initially it was only the contribution from the electronics, but then we said that there can be other terms which will have time dependent properties but not frequency dependent. So I can club all of them together here. So these are antenna based gains because you have the A and B sitting over there. Then I have the band pass, which are a function of frequencies. So these are the gains that depend on frequencies only. And again, it can be different in different antennas. Then inside the integral, I have this thing which I said is a kind of isotropic, in the sense that if I look at the center of the field of view with respect to that, it doesn't change if I go around, but it can change as I move from the center of the field of view towards the edge of the field of view. So that is this term. And then I have these quantities which depends on the antennas, depends on the direction at which you are looking at. Because they depends on the antennas, or anything here which depends on the antennas can also depend on XA and XB. So these two depends on XA and XB, and it can depend on frequency and time, everything. So those we call the direction dependent gains. These gains are time dependent gains, so there is no frequency dependency and no direction dependence. There is no direction dependence here, but these are only frequency dependent, and these gains are direction dependent. So they can have both frequency, time, and direction dependence. And then, of course, any electronics will add some noise to the system. It's not only electronics that adds noise to the system. Even at the low frequencies, the largest part of the noise comes from the sky. Because when you are trying to look at in one direction in the sky, there is the antenna receives radiation from many other things, and all those contribute to the noise in the system. So that is the noise term. Okay. Now, if I forget about all the gains for the time being, so this is one. By the way, the gains are supposed to be one, right? A good gain is one. Then you don't need to bother about it. So all these gains, if I consider them to be one, the time dependence is one everywhere. Frequency dependence is one everywhere, the direction dependence is one everywhere. I forget the noise term. Then the visibilities, then what I get in the left hand side, the voltage correlation is equals to the visibility, which is given over here. But this, if you look at in the right hand side, by the way, what are these integrations? I have not written the integration limits. What are these integrations over? Theta. So these are essentially over the solid angles, right? So d n cap. So if I decompose my n cap, which is the unit vector, in terms of the coordinate system that you have been talking about, if the z direction is at the center of the field of view, x and y directions are on the plane of the sky, or the tangential plane of the sky, right at the three components of the unit vector is this. These are the direction cosines. Because this is a unit vector, this has to add up to 1, remember? Right. So when I say dn cap, you can figure out that this will be an integral like this. Same thing, somebody else can write as d omega is again solid angle, and that you know is sin theta, d theta, d phi. Same thing. Polar coordinate system. And then when I have that u dot n cap over there, this u, which I have written small u, is remember that this is xp minus xa by the observing wavelength. There are three components. N has three components which you can here. Which essentially means, if I look at this integral now, this integral is not quite a Fourier transform integral. And there is one more thing which I originally wanted to point out, that the limit of these integrals, what is the limit of L and N? What are the limits of L and N? 0 and 1? Minus 1 to plus 1. And going the other way. Okay. So even these integrals are not minus infinity to plus infinity, but those integrals are from 0 to 1. So only in certain circumstances. So let's say that that A theta, which is A n cap, sitting over there. This A n cap sitting over here, which is the effect of the antenna. If this thing is very small response around the center of the field of view, then what happens? Then even though the integral limits are from -1 to +1, I can push them to minus infinity to plus infinity. Because anyway, after say the L or M equals to say 0.1, the contribution is 0 from here. So in that case, okay, so then I can push the integral limit to minus infinity and plus infinity. But still, that term will have this small u, the two components in the plane of the sky, if I write capital U, and the component of n cap in the plane of the sky, remember, is theta. I'll get that, but then there will be another correction term. Right? We'll come back to that later. So you see that the visibility that we wrote when we are trying to calculate the power spectrum is, we said, is a Fourier transform of delta I theta times a theta, but it is not quite so. So there is caveats there. So which one has to take care of while actually finding out these things. Now, for the time being, the first thing that one has to do is to calibrate this. So this is the voltage correlation that you get. I said if you get all the gains equals to 1, then you get that. Right? But how do you make all the gain equals to 1? Well, you find them and you divide by them. Right? So that process is called calibration. You have to calibrate. Now once you try to calibrate, then you realize that the calibration is an iterative process and all these things. So there is time variation there, and then there was time variation here, which was the direction dependent thing. And then you realize that large time scale variations, this particular case, also have larger amplitude. Okay, so if I go back, here the gains can have variations at smaller time scale, larger time scale. These can have variations at smaller time scale, larger time scale. First thing is that even in case of low radio frequencies, the effect of these gains are much smaller than the effect of that gain. Means that this will be more close to 1 compared to this. Okay, if that is true, then for the time being, first what I will say is that I am doing an iterative process, so I will assume this to be 1. The direction dependent gains to be 1. So once I do that, I get this. The direction dependent gains are 1, but I have to still take care of these. But then for these gains which are function of time, there is a large time scale variation and there is small time scale variation. So that is like given in this cartoon here, where this blue line is a large amplitude variation which is also at a larger time scale. Like at small scale, so this is just the x-axis is that. This is completely arbitrary plot, even generated by ChatGPT in the morning. I was making the slide, I realized that I can make use of that. So it's like 0 to 120 seconds. And this variation is over like 100 seconds, even more. But then there is this small time scale variation. They're happening at 10 second scale. Right? So the full thing is this. But then what I will do, again, what I have been doing so far is that I will not look at the small time scale variation, which has also smaller amplitude. I will just average over a certain range of time and put a point over there, because this faster oscillations will cancel out. And put a point over there, put a point over there, etc. So what you do is the following. You do something called the primary calibration. So primary calibration is once again to use a field in the sky which has compact sources, and these compact sources, about these sources you know already. Mostly you use a field where you have one compact source which is very high in amplitude, or its flux is very large compared to all the other sources. Such that if I look at for smaller amount of time, then I will only see that single point source. And I know its amplitude, I know its position, which means that I know this quantity. If I know this quantity and forget about the noise again for the time being, then I can now figure out what are these. And because now when I say that I will look at that field in the sky which has this single point source which has very large amplitude compared to the others, it may be some random direction in the sky, not the direction I am interested to look at. Then what will happen? Then I can look at in that direction only after a certain time. Otherwise, I will only look at the calibrator source. I will not do anything with the H1, right? So I have to go back and forth between my calibrator and the source that I am interested to observe, which means I can only look at the calibrator at a certain after certain time. So like this, in this case, it is done after every say 20 minutes. So every 20 minutes you calibrate for the gain, so you can only take care of the large time scale variation of the gain. And once that is taken care of, then what you will be left with is this. This is a small time scale variation. This I cannot calibrate using those calibrator sources, which are called primary calibrators. So I have to do something else. Okay, say I have this gain. I have this gain T as a function of T. So I am saying is that this T as a function of T for interferometers has a variation of time scale of minutes or even tens of minutes, and has a variation which is at a much smaller time scale. Okay. It turns out that the variation which is at a larger time also has a larger amplitude. So what I can do is I can take care of that first. Okay. So this blue line over here, if it is blue, is the variation at a larger amplitude. So that I take care of first, and serves a larger time scale. Once that is taken care of by doing the primary calibration, then only this is there. So now I have to look at it. Any other question? So there are some sources which are regularly observed by some certain telescopes, so that you know about. I'll not. We can discuss it outside because that will take a lot of time to. That is a different thing. So you have to know what is that function A. So you need that, and then drone is being used very recently with GMRT. Know what is this function. Because after doing all of these, what you will know is A times I. To extract I out of it, you need to then know what is A. A is a property of your telescope. We should be able to calibrate it. This is A times I. All that I'm talking about is A times I. Okay. So now, okay, so as we said that any calibration requires you to know about something for which you actually know what you are trying to measure, right? Calibration meaning of calibration is that. Like for example, if I ask you to measure the length of this room using this stick, you can only say how many times of this stick the length of the room is, not in meters per second. For that you have to know the size of this stick. So similarly, when I talked about these compact sources in the field, in a different field, so you know about them. But then when you are looking at these smaller scale variations, how do you calibrate those? The idea is that after you have done the large time scale variation, which has taken care of the most of the amplitude of this gain, now you have kind of the left hand side is roughly equals to the visibility. Very small effects of these are still there, but roughly it is equals to the visibility. Once this is roughly equals to the visibility, so I can use the field that I am looking at as my calibrator source. Okay, and then try to figure out that if I use that as a model for the calibrator source, If I want to do that, I have to make an image of that sky, right? I use that model, which is the image of the sky, as my calibrator source, and against that I calibrate my visibility. So I make an image, put that back in here, and against that I can try to calibrate that. Now the process is much more involved that I'm trying to make it out here, but it is called a self-calibration. And you actually does not, most of the cases, it doesn't use the entire sky. What you do is then again, in any direction you look at in with a radio telescope, you always see a huge amount of large number of radio galaxies. These radio galaxies are compact sources which are there at different positions in the sky. Compact means they're not extended. Extended and compact are the antonyms to each other in this. So because I can figure out where they are at different directions in the sky, I can take the brightest one, leave all the other sources apart, so I subtract them out, so I have only one bright source now, and then I calibrate my visibility with respect to that. Just like I use it as my calibrator source, and keep on doing it in different directions, etc. So then you get the self-calibration done. Now, as I said, that for this you need to make an image. That has this problem. To make an image, remember that you are measuring this thing. What is written over here is again it depends on these two antennas. So the baselines are measured only at the positions which are given by the antennas. And then there are another pair of antenna which gives another baseline. Remember, then again, U is a projection of those along this plane of the sky, which means as the sky rotates as the source rises and sets, you get different projections and you make different baselines. But after all of these, you don't have the entire visibility function measured. It's only measured at certain points in terms of U. I will try to make the image out of it. There comes a lot of artifacts because of that, because it is not completely measured at all points. Essentially, what you do is you use an algorithm which interpolates the measurements where it is not done. And this is a serious problem in any measurement, which requires you to do Fourier transform. So let me just emphasize a little bit, because this is one of the track of the story. Let's say that, talking about probabilities for the time being, let's say that I have a function fx as a function of x, and this is how the function looks like. Okay. And what I am interested in is the power spectrum of the function x. And if you remember that this is roughly proportional to delta k x tilde k squared. X tilde k is the Fourier transform of x as a function of f tilde k squared. So f as a function of x, Fourier transform that is f tilde k. Now, in my ring, I can measure it at regular intervals. Then given the nice criteria, I will be able to reproduce this quite well. Depending on what is the range in x in which you have measured and what is delta x, I still will be able to reproduce this function t as a function. But if now I have certain measurements missing, let's say that missing there and missing there, and then what you will see is that this gets convolved with something, some function which you call the sampling function. And then these places, because it is missing, if you want to get back to these functions, I have to assume the values here. The way I assume those values, the way I interpolate those values, depending on that, I will reproduce this function. Completely depends on how we have done. Now this happens, you can think of x as the baseline plane and fk as the image. Then there will be a problem in the image. Similarly, remember that I want to also measure the intensity as a function of frequency. And they want to go to the tau space. Remember that tau is the Fourier conjugate of the frequency. Tau spectrum is a function of tau. So in the frequency space, if I have certain channels means frequencies, where the measurements are not done for some reason, that telescope which cannot do measurements because of, I don't want to go into why, but you can ask for why you have to flag certain channels. So then again, when I want to go to the tau space, calculate the power spectrum as a function of k parallel. Remember, k parallel is proportional to tau. I'll have the same problem. It's a measurement problem which always is there, and one has to be careful about it. So that is what I mean that. So the kind of way of getting a better image is called deconvolution. I think Srijita will show you some examples of that, right? Now, if I ask you that I want to reproduce this from what I have measured, the visibilities, it's still okay if I have only a few point sources or compact sources in the sky. Because if I ask you for one source in the sky, what will be the visibility? One point source can be represented by three numbers. One is its flux density, is the amplitude of the source, and where the source is in the sky. Two numbers, right? Three numbers. So only three numbers. If I measure 10,000 visibilities out of that, reproducing three numbers is not that bad. If I have, instead of one, I have 100 point sources, still it is only 300 numbers. If you measure 1,000 visibility, it is still not bad. So this deconvolution works fairly well for point or compact sources. However, if I have diffused emission, it does not work at all. If you are missing these lines, then you will always get something which depends on you, not the sky. Okay. So the other problem I said is that one is that you have to make an image to do the calibration. Remember the self-calibration requires you to make an image. The other problem we were talking about, we were trying to hint it there as well in the whiteboard, is that that expression is not quite a Fourier transform. So let's look at that expression in a little bit more detail. So now what I have done is I have expressed U in terms of its components, which is U, V, and W. U is a component along east-west direction, V is a component along north-south direction, W is a component along the line of sight, and then the Dn integral looks like this, which we had written there as well. A n cap looks like this, I n cap looks like this, so this I or delta I is same thing for me. And then in the exponent, U dot n cap becomes UL plus Bn plus Wn, but remember that n is related to L and M in this way. So this L square plus M square plus N square equals to 1. So that is what is sitting over. If I try to figure out what are these different quantities, so this is again, this should be L square, this should not be there, but in fact, this quantity, xp minus xa by lambda, is my small u, just sitting over there. The component of that along the line of sight is W. The component of that parallel to the line of sight to the plane of the sky is capital U. It also means W is, what is W next? Then W is xp minus xa dot n0 cap by lambda. So W will be xp minus xa, which is minus 9 divided by lambda. So this quantity that we will call it B. Then B by lambda. But now again, if I ask you how much time, so this you see that this if there is a point source very far away in the field of view, and this is the direction of the point source, there is a plane wave that you will see at the time at the point where there is an antenna, right? Spherical wave will be emitted from the point source. If you are very far away, you will sample only a very small part of that sphere, which is a plane. So that looks like a plane wave. So the plane wave, the equal phase surface will be like this. So the same phase will reach this antenna earlier than that antenna. How much that will be? Well, that will be again given by xb minus xa dot n0 cap, which is this distance divided by c. Right? So that is the delay that happens to reach to antenna. So that tau is again b dot n0 cap by c. Now if I relate this to these two, I say that tau is equals to b by n0 cap dot n0 cap by lambda into lambda by c is how much? Mu. Lambda by c is 1 by mu. Omega by w by mu, not omega, w by mu. You see, this w is related to the delay, and u and v is the vector in the plane of the sky. Remember that when we were talking about the power spectrum was given in terms of capital U vector and the delay tau. So now you see that there is the visibility itself is related to capital U vector and the delay tau. Okay. So now the question is, the problem here is that this is not a Fourier transform. The two problems, one is this integral goes from -1 to +1. The other problem is this term. It's a very complicated term, which we sometimes call the W term. Comes because of non-zero values of W. So what do I do? How do I take care of it? So what I do is, I first say that I will break. So I can have a telescope which has a very large field of view. So if I have a telescope which has a large field of view, I cannot do that approximation where I say that -1 to +1 is equivalent to -infinity to +infinity. So what I do, I break that field of view into small parts in the sky. Those are called, they're called different things in different cases. I'll call them W projection planes. So basically, I have a hemisphere, I break it up in terms of polyhedrons. Okay, we have seen heel tips, right? It does a similar thing, but it is mathematically it does a similar thing, but it is not exactly the same. So now if I look at each of these small field of view, they are small. For each of this field of view, I can represent my integral as -infinity to +infinity. The size of the field of view has reduced. Why the size of the field of view has reduced? Because I've broken the field of view to smaller places. Now, because I have broken it into smaller places, smaller field of views, this L square plus M square, what is L square plus M square by the way? The L and M. So I have this vector theta, right? L is like sin theta x, M is like sin theta y. So theta, the two-dimensional vector in the sky plane in the sky, components theta x and theta y. So these are like this. So this. So if theta x and theta y are small, then you see that L square plus M square is essentially theta square. Right? So field of view small means L square plus L square is small. So for each of these W projection planes, I can now do a expansion of this root over of 1 minus L square plus M square. I can write that as two terms. One is 1, one is L square plus M square by 2. And then what I do is I multiply this side by e to the power I 2 pi W, such that I can get rid of this thing. So once I do this, the left hand side I have something I will call W prime, sorry, V prime, which is a function of U, V and W. In the frequency dependence for the time being, you have to do this for each frequency separately. In the right hand side, I have this entire thing multiplied by e to the power I 2 pi w times L square plus n square by 2. Right? Then I do this, I define this, which doesn't have this extra term. And I define a new thing called capital G, which is a Fourier transform of this extra term only. Or you can think of it in the following way. This is the Fourier kernel. This quantity in the left hand side is a Fourier transform of A times I multiplied by this thing. Right? If I go to the Fourier domain, then it will be a convolution of the integral up to this and G. The integral up to this is the visibility if W equals to 0. So that's what I have written here. Purely W equals to 0. And the rest of the thing is the G. And this, remember, I have to do for each of these W projection planes separately. So now this E prime, which is now in the function of U, V and W, is a convolution of this quantity with G. There is probably a little bit of this thing which should not be there. Once I have defined it as a V prime, that already includes to the I2 pi W, so that is a mistake. But otherwise, you can see now the full W term visibility is the visibility with W equals to 0 convolved with this quantity. What is the visibility with W equals to 0? Well, if I am looking at this direction, which is that, remember that I have broken my field of view into many small facets or many small W projection planes. So this is towards one of these W projection planes. So along, if I look at that as the line of sight, that as the line of sight, so my sky is perpendicular to that like this. And if I consider the visibility only like that, so that is this thing, because the W is 0. If my antenna was not here, but the antenna was there, the W will be 0. Right? So that is this term. So without this convolution, what happens is that you get a visibility, which is the case when the signal is converged up to this plane. And then the signal is calculated at this plane. And then this convolution projects that into the actual plane where the antennas are. So that's why this algorithm has a name, it's called the W projection. You calculate first at the plane which is parallel to the sky for that particular W projection plane, and then convolves, then translates it to the plane of the antennas. Okay, so that is that takes care of the fact that the original relation is not a Fourier transform relation, but now with these approximations you can actually estimate the sky intensity. I should ask the question that how should I decide how many planes in which I will divide my entire sky? That will depend on the kind of noise you have in your measurement or the accuracy at which you want to measure things. If you are dividing it to smaller and smaller facets, obviously this approximation where I have changed the square root to something is more better, but then you have a lot of time to do the computation, because you have to make an image for each of those planes. Okay, so that is required when you are trying to do the secondary calibration and self calibration, where you are making an image of the field. So you see that, remember when we said that we are measuring the H1 power spectrum, it was directly proportional to the measured quantity, which is visibility, the square of that, right? Visibility square was directly proportional to the power spectrum. But then you realize, to get the visibility, you have to calibrate the data. To do the calibration at smaller time scale, you need to make an image. So the self calibration requires an image. Okay. So there is no you have to make an image. You have to make an image for two different reasons, but that is one of the reasons. Okay, so this was the full measurement equation, remember? Actually, this is not the full measurement equation. Can you tell me what is missing? What was missing from our entire analysis? That we said that we will do the most rigorous Van-Sitter-Janicke theorem, but then we missed. We have done only 1/4 of it. What are the other three? Delay is there already. Delay is there in that object. I said one. We have done 1/4. What are the other three? Ionosphere is there in that curly B. We are doing only one polarization. So you have R and L polarizations, right? Or X and Y polarizations. So when you are doing this voltage correlation, you are correlating with the X polarization with the X or R with R. But then it can be R with L, L with R, L with L, all four of them. And then remember, these gains are calculating R with R, etc. But then there is, when you talk about calibrating for the polarization also, there is something called polarization leakage, which is that the signal which you should have detected in R, part of that goes to the L polarization. So if there is polarization leakage, then you have to take care of. So that part is not considered at all. But it turns out the effect of these gains is much higher than the effect of polarization decay. So one should do this anyway first and then look at the decay. Okay. So we say that by doing all the things that we have been talking about, the effect of these two terms are taken care of. Not talked about Van-Post calibration in detail, but say that that is also done. But while doing that, I have assumed that the direction dependence gains are 1. Just because we said that they have lesser effect. So now once we have taken care of the things which are outside the integral, I need to look at the direction dependent gains. So now my measurement equations taken care of these, so those are not there. I have the direction dependence gain only. And again, I have neglected the noise just for simplicity. Yeah. Which omega? One second. Where is W? Yeah, it is time dependent. So basically the projection changes. This N0 cap is fixed in the sky. The sky gets, because of that this projection changes. But see, it is not fast time dependence, it's a slow time dependence. When you calculate the gain, you calculate for each time. So I need to know how to calculate for the direction dependent gain. So what we do is the following. So first, this we have done. Do imaging and deconvolve for a model sky. There are kind of idea about what is the time. There are these errors, but remember all the other errors we have taken care of. So this all the other gains. So this you have a kind of idea. This will always have certain bright sources, as we said. For the self calibration also, you have used those bright sources. But now the gain, because of these different bright sources and different directions are different. So that is why we call it direction dependent gains, right? The curly D is dependent on n cap. So what do? What I do is the following. I remove all the other bright sources, keep only one, which is not at the center of the field of view, but somewhere else. I now move my field of view electronically, means that I change this factor so that I move and make that point source at the center of my field of view. If I do that, then you can see, you can do this integral. So this n cap is the direction of that source. So the point source with I0 intensity and at the direction n cap will look like this. You can now do the integral. Once you do the integral, you have these two combined. And now this is something you have measured. I0 is something you know. The direction of the source in the sky, so that also you know. I can figure out this. Now again, all the time you try to figure out the gain, you only get the gain which is multiplied for two different antennas. And then there are things called phase closure and amplitude closure which you use to figure out the direction dependent gain. I will request you to look at those because there's not any time to go through them separately. Yeah. You subtract all but one point source, self-calibrate for the source left, apply the gains to the entire field, and repeat with other types. That was your question. And you have done it anyway, you know, but it's a good point to point out that see, one point source which is not at the center of the field of view, it's at some certain direction in cap, will calibrate for the gain, the direction dependent gain error along that direction. Right? Now I have to figure out the direction dependent gain from all different directions and take care of them one by one. Okay. Again, remember that the direction dependent gain is coming because there is an ionospheric stream is everywhere in the sky and it is supposed to be different at every direction. Calibrate for that, I am supposed to have one point source in every direction. There's the entire sky full of point sources. It's never there. You assume that the variation of the ionospheric stream is very smooth such that if I can calculate it only at few different directions, then I can know what is the variation. And after you do all of these, there is obviously some gain errors which are left. That is never calibrated because you don't have enough measurement of the actual sky to calibrate the gain, and because you have always a noise transfer. So whatever you do is up to a noise limit. So all those leftover gains becomes a nuisance for your observation. And if you want to know anything about them, you ask straight up. Okay, so what are the challenges? After I do all these, I calibrate for all the visibilities and all. Don't need to take pictures because I've already uploaded this I've already uploaded the slides in the classroom. Okay. So let's ask the question, what are the challenges? And in the afternoon lecture, we'll try to take care of some of these challenges. I mean, obviously, all of the challenges are not taken care of. If it was, then you would have seen the H1 signal measure. The foregrounds we have learned about. And again, as an observer, I need to know where are these signals coming from, but I don't need to nitpick. I need to know only the properties of the signal. Like if I tell you, if somebody tells me that there are 5 different ways you can generate a point source, but all those sources has the same observational property, as an observer, I am fine. I will catalog that as one type of source. Whether it's coming from a quasar or whatever you think of, it doesn't matter. So I have compact sources and I have diffuse sources. This kind. The compact sources, again, both of them actually can be inside the field of view of the telescope, and that can be outside the field of view of the telescope. Now, when I say outside the field of view, the response of the antenna outside the field of view is never zero. It is always something non-zero. Okay. Very small, but still non-zero. If you remember that yesterday we were looking at the antenna in the other room, and you have the Yagi antenna. They had a reflector at the one side, and then you have the other things. Once you rotate it, you have to get the maximum response when the Yagi is the entire Yagi is parallel to the dipole that is receiving it. As you rotate it, the response reduces, but it never goes to zero. That never goes to zero is not because there is some electronic error in there. It is also because that the antenna radiates something in those directions. So that's the problem, because you see, maybe it radiates 100 times less in that direction or receives signals multiplying the signal by 100 times less in a direction which is outside the field of view. But then, if that is a foreground, which is 10 to the 4 times your H1 signal, then 10 to the 4 times 100 is 100. 10 to the 10 to the 4 times 1 by 100 is still 100. Right? So it's still 100 times more than your H1 signal. So that will cause a problem. You have to look at this type of problem is more for the compact sources, because the diffuse emission is it really doesn't do that much. It does, but you will see that why I said it doesn't do that much, but mostly for the compact sources. So in field of view sources, one can take care of, because remember that way, for the point sources, you can make a nice image. Once you make that image, you can take care of that image. You can subtract the visibility contribution of that image from your observed visibility. They have now reduced or subtracted the point source foreground. Only those sources which you could have made the image, because they are inside your field of view. The sources which are outside, they are too faint to make an image. They are still there. Their contribution in the field of view is still there. That you have not taken care. So that's outside. And then you have the diffuse emission. Okay. Now, how do I address this question? How do I separate out the foregrounds from the H1 signal? Turns out that the H1 signal has a property which is completely different from the properties of the foreground. The property is the following. Remember that we correlated the visibilities at two different frequencies. It is that correlated the visibilities at a frequency separation. Now that is what I plot in the x-axis. And the y-axis I plot the frequency decorrelation, or that basically that visibility which is correlated at two different frequency separation. Now, if that visibility is the 21 centimeter signal, then it is shown that it goes down very sharp. Goes down to 0, almost like 0.5 to 1 megahertz within that region. This is again a cartoon. This is not the exact plot. Exact plot I think Srijita will show you, but exact plot means that plot from the model Srijita will show you. But the idea is that it goes to 0 very fast. But why is that the case? Because imagine that you have a 21 centimeter cloud sitting somewhere in the sky. Okay, even not a cloud, but a screen of 21 centimeter at a certain redshift. Now, that 21 centimeter screen is not emitting at only one frequency, but it's also emitting at the nearby frequencies, because you have a certain temperature of that gas. So it is Doppler shifted to the nearby frequency. If I correlate the screen, the 21 centimeter screen at a certain Z and the nearby Zs, by correlating the 21 centimeter screen at visibilities at two different frequencies, I'm actually looking at the same gas. And the difference is because of the thermal motion. But then if this is too much, Z is too much different, but the frequency is too much different, then I'll start to see another layer of this 21 centimeter. That layer will not be correlated with the previous layer. Right. So once the frequency separation is high, the correlation goes to 0. Only within certain range it remains correlated. On the other hand, all the foreground signals, this happens for the 21 centimeter signal because it's a line emission. Right? The actual emission peaks at a given line, and then because of thermal broadening, it goes on a little bit there, here and there. But it's a synchrotron emission, it happens at all frequencies or any other foreground emission. So this decorrelation is not there. It's almost constant across the separation. That I can now use, because now what I will do is I will calculate my CL, or I will calculate my visibility correlation at a frequency separation of say 2 megahertz. The only thing that I will be left with is the foreground. Subtract the foreground, then I will get this. Right? Get the idea. So here both of them has an amplitude 1, which is not correct, because it's only I am looking at the frequency decorrelation. This curve will have an amplitude which is 10,000 compared to 1. So the signal that I will see here is 10,001. The signal that I will see here is 10,000. So we subtract 10,000 from 10,001 to get 1. Correlation is really different. Decorrelation is
Here is L dependent.
It is L dependent. There are many other
L
things.
is larger.
Yeah.
Okay, so we know that.
So to do it for all L, each L separately.
Really should have a model that is range.
Yes. And that's why I said this is a cartoon.
Also.
Quite false or faster. It is because, see, when you are looking at two different frequencies, go to the next slide. Maybe the next slide. Then you will see the answer will be easier. And then there are other problems. One is called the antenna crosstalks. This happens to the antennas which are nearby. And then this receives a signal and then it tries to radiates a little bit, which is picked up by the other antenna and so on. So this always happens with the antennas which are nearby in a radio interferometric array. And the crosstalk is extremely small, so you don't care. But then again, foreground giving a crosstalk between two antennas becomes very loud compared to the H1 signal, which is that if I speak very less loudly and you start doing crosstalk, then you will not be able to hear me. And then there are calibration errors. Ask speaker. Okay, this is the last slide. So remember that we had, this is an expression we wrote in the first or the second lecture, end of the second lecture. We have correlated visibility, two visibilities at certain frequency and the frequency separation, the Fourier transform of that was tau, which we have related to the delay today or dW. And this is something which is a property of the 21 centimeter signal. So this I have again written, whatever is written in that whiteboard, that is again copied here. This frequency over here, around which that frequency separation was taken, actually gives you the redshift to the redshift to where you are observing. Okay. So if I have these antennas, what I am thinking of is a box. This box has like x, y, z. If I do the Fourier transform along all these three axes, I will get kx, ky, kz. The kz is along this direction, right? And the box is at a redshift z, which gives you that frequency nu, observing frequency nu. And then to answer Showik's question, you can think of this part of the box, which is at one z, means at one side of this box, and the other part of the box, which is at another z. So this is at one frequency, that other is at another frequency. Question is that if I correlate the visibilities from here and that side, will they be correlated? If this only emits at 21 centimeter redshifted to that frequency, and this only emits at 21 centimeter redshifted to the other frequency, they will never be correlated because these are two random fields, two different regions in the sky. They will be correlated if this 21 centimeter whatever H1 has a thermal broadening, and that thermal broadening gives you a little bit emission corresponds to that frequency as well. Okay, so now you can see that as you can separate out the box of this frequency or the Z, the correlation happens. Okay, so as I said, so that will be the last slide. So what we will do in the next is to see how this can be measured. That, and then I am not an expert in this. The two experts of this are sitting in the audience. One is Vijita, the other is Asif, and the other expert is coming. Other expert is the SOC chair, who is coming in 2 days. So all the questions from the next talk, you can ask them once they come. Why it will be correlated? Answer that question then. Because the foreground is an emission which happens at all frequencies. The same magnetic field and electron combination gives you radiation at all frequencies. So now, so there is a distribution of these electrons across the sky. Each of them is giving radiation at all frequencies. You get a box where each frequency corresponds to all the same electrons. Now in this box, each slice corresponds to a different set of H1. So different sets are not correlated. But they still become a little bit correlated because this set of H1 also emits a little bit in the nearby frequency because of thermal burning and all.
It's like really
That's why I said the other things which I don't want to go into. See, we also have correlation between the H1 and two different slices, actual correlation, because of cosmological reason. The power spectrum that you are trying to measure is telling you that there is certain correlation. But again, that correlation will also fall off as we go further and further. I gave an easier answer. Any other question? Prabha is waiting.